Let's begin section 2.4 today, which is finding zeros of a polynomial function. So recently we've been doing this, but the problem has been giving us one or two zeros, and then we've been finding the rest. What happens if we aren't given any zeros? So to do this, what we're going to do is we're going to start with something called the rational zeros theorem. It tells us how to find possible rational real zeros. Okay? So you can see the rational zeros theorem basically saying if we have a function, then what we do is we make what's called a PQ list, a P over Q list. Okay, P is a factor of the constant A0, and Q is a factor of the leading coefficient A sub n. Okay, so here possible rational zeros are going to be factors of A sub 0, which is our leading coefficient, divided by the factors of A sub n, which is our leading coefficient. So constant over leading coefficient. So let's get started and just try this for a second. So list the possible rational zeros. It's already in descending order, so that's good. This is our constant. So factors of our constant are plus or minus 1, 3, 5, and 15. And then factors of our leading coefficient are plus or minus 1 and 2. To sum that up, all of our possibilities will be all the numerator over all the denominator. So 1 over 1, 3 over 1, 5 over 1, 15 over 1, but also 1 over 2, 3 over 2, 5 over 2, and 15 over 2. So we have a total of 16 possible rational zeros. And obviously not all of them can be. There might be one of them, or might be 3 of them, but there can't be 0, or there can't be 16. All right, so pause the video there and go ahead and try B. So you have factors of 5 over factors of 4. That would give us plus or minus 1 or 5, or 1/2 or 5/2, or 1/4 or 5/4. So here it looks like we have a total of 12 possibilities. Let's apply that. Example 2 says state the maximum number of real solutions. Well, this is a cubic function, so the most there could be is 3. Like I said, there could be 1, but the most there could be is 3. The rational zeros theorem says plus or minus 1, 2, 3, and 6 over plus or minus 1. So that would just be plus or minus 1, 2, 3, and 6. So we have 8 possibilities. Now the fun part. There's no way of knowing which of those is going to work. So it's time to start playing guess and check time. Okay? How do we guess? We set up syntactic division. And we just pick one of our 8 possibilities. So positive 1, 2, 3, or 6, or negative 1, 2, 3, or 6, and start trying it. And if it doesn't work, we erase it and start over again. So let's try positive 1. And we got lucky that positive 1 worked. So now I can write my equation, my original equation, as x minus 1 times x squared minus x minus 6 equals 0. Continuing to factor, now I know my 3 answers are positive 1, positive 3, negative 2. Hopefully next time we'll guess wrong. Number 3. Possible number of zeros would be 4. And our possibilities would be 1, 2, 3, 4, 6, and 12 over 1 and 2. So lots of possibilities here. So 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1. And then also 1 over 2, 2 over 2 we already got because that's 1. 3 over 2, 4 over 2 we got because that's 2. And 6 over 2 is 3. And 12 over 2 is 6. So we're good. But that still leaves us with 16 possibilities. So let's set up our syntactic division and start guessing. Now this time, we have to find 2 correct answers before we can move on. Because this is a quartic equation, we need to find 2 to get it down to a quadratic. So again, let's just play the guessing game. And let's start with positive 1. And man, we got lucky again. That's one answer. But, again, because this is a quartic, we have to find another one. Okay? So remember, when you do this, don't go to the original equation anymore. Start with this secondary equation now. So we already used 1. Let's try another one now. Let's try 2. And man, we are really getting lucky today. Both 1 and 2 work. So now I can rewrite my equation of f of x equals x minus 1, x minus 2, 2x squared plus x minus 6. And continuing to factor, if we can. Let's see if this factors here. It will. It'll factor like that. 2x minus 3 and x plus 2. So our 4 zeros in any order here. 1, 2, 3 halves, and negative 2. And then part D says to write that in factored form. We already did that. So let's just cheat a little bit here. And there's our factored form. Example 4 here, I already kind of got started on it. I'm pretty sure at this point A and B are good. So let's go ahead and try part C. Now to do this, I'm going to purposely guess wrong here so you can see what happens when you guess wrong. So I'm going to try negative 3. I'm not going to fill in that last one because I know it's not negative 9. So clearly this is not going to be 0 here. That's no problem. You just start over again. Just erase that, especially since you're on this iPad here, and try something else. So let's try 1. And negative 9, so that gives us 0, so 1 works. Okay, so this one is actually a pretty tricky problem here, because if you tried negative 1, positive 3, positive 9, negative 9, none of those would work, okay? But we need to find 2 of them because this is a quartic, and we've only found 1. But remember this chapter, we've been talking about multiplicity a lot. A 0 can occur more than once. So what happens if we try 1 again? It works again. So I can rewrite my function now as x minus 1 squared times x squared plus 9. And that actually is completely factored form. We cannot factor that x squared plus 9. Now let's answer C. I already know x minus 1 will give us x equals 1 twice, but you don't have to write it twice. And x squared plus 9 equals 0. That does not factor, so we just have to subtract the 9 over. And we get plus or minus 3i. So x equals 1, and then plus or minus 3i. All right, at this point, why don't you pause the video and try number 5 on your own. And once you've completed it, come back and check your answers. And there we have the answers for number 5. Feel free to pause the video and look it over at your convenience. And that would end the first day of notes. So now we're going to look at day 2. We're just kind of going backwards. If we're given zeros, rewriting the original equation that it came from. Okay? So the fundamental theorem of algebra says that every polynomial function has at least one zero, real or imaginary, in a complex number system. And then the linear factorization theorems, we can write those functions as factors of their linear, linear factors of the original function. Okay? So this one says, write a polynomial function of least degree with real coefficients in standard form that has zeros 1, 2, and 3. So it's called f of x, so we're going to call it f of x. And I know it's going to be x minus 1, x minus 2, x minus 3. Because those are the zeros. So to simplify this, we can just multiply x minus 1 times x minus 2. We get x squared minus 3x plus 2 times x minus 3. And we can keep going by multiplying that out as well. So it gives us x cubed minus 3x squared minus 3x squared plus 9x plus 2x minus 6. Combined like terms gives us that as our final answer. So that function is a polynomial function of least degree with real coefficients in standard form that has zeros 1, 2, and 3. All right, this next theorem says, conjugate pairs theorem, if a function has a complex polynomial a plus bi is a 0, then a minus bi is also a 0. Okay, so only imaginary numbers. It only works for imaginary numbers, not for real numbers. Okay, so example 2 is just asking us to find all the zeros. So degree 3 means we should have 3 total zeros. 2 of them are given to us. But since the second one is imaginary, I also know that 1 minus 3i is also a 0. So there's your zeros, 1, 2, and 3. Part B, we should have 4 zeros. 3 of them are given to you, but one of them is imaginary, so we know its partner, its conjugate, positive 4i, is also a 0. So there's your 4th zero. And finally, part C has 5 zeros. Only 3 of them are given to you, but 2 of them are imaginary. So I know 2 minus I and negative 5 plus 2i would be our 4th and 5th zeros. So we're going to use that moving forward in these last couple slides here. So number 3 says, write a polynomial function of least degree with real coefficients in standard form that has those zeros given to you. But it actually gives us a 3rd zero. It actually would give us this 0 as well. So that means there's 3 zeros. Our final answer should be a cubic function. So let's start by writing it out like so. G of x equals x plus 3, x minus 2i, and x minus negative 2i, which we can just write as x plus 2i. Always start by multiplying together your conjugate pairs first. So now g of x equals x plus 3 times x squared plus 4. If you don't know how we got that, just multiply it out one step at a time. Your middle 2 terms will cancel out, and your last term would become positive 4. Now we can multiply these together. And we would get that for g of x. All right, example 4 tells us 3 answers, but it actually tells us a 4th answer as well. The opposite of I would be negative I. So let's write out our function h of x. X minus 5, x minus 2, x minus I, and x minus negative I, or x plus I. So I'm going to do 2 steps in one here. I'm going to multiply the 2 real parts together to get x squared minus 7x plus 10. And multiply the 2 imaginary parts together to get x squared plus 1. And now we can multiply the real and imaginary parts together. X to the 4th plus x squared minus 7x cubed minus 7x plus 10x squared plus 10. Combining some like terms and writing in descending order gives us our final answer for that. Okay, example 5, write a polynomial function p of x with these zeros. So again, they're technically giving us 3 of them here. Negative 4, 2 plus 4i, but also 2 minus 4i. So write your function out. X plus 4, x minus 2 plus 4i, x minus 2 minus 4i. Take your time with this one. Lots of work to do. Just do one step at a time. First, I'm just going to simplify by distributing those 2 negative signs. Now I'm going to multiply together the 2 imaginary parts, leaving the x plus 4 out in front. A lot going on there. But now we can see negative 2x and negative 2x. We can combine those like terms. We'll do that in a second. Positive 4ix and negative 4ix will cancel out. But also, negative 8i and positive 8i will cancel out. And finally, negative 16i squared is basically just plus 16. So what we end up with here is x plus 4 times x squared minus 2x is minus 4x plus 4 plus 16, so plus 20. And now we can multiply these 2 together. So distributing the x gives us x cubed minus 4x squared plus 20x. Distributing 4 gives us 4x squared minus 16x plus 80. So our final answer, after combining like terms and simplifying and writing in descending order, the x squareds actually cancel out here. I missed an x. There. So I would get plus 4x plus 80. All right, last one. It says zeros of 3 minus 3i, so that's also 3 plus 3i. and 2 with multiplicity 2. So that means 2 and then 2 again. So we have 4 zeros here. Let's start by writing that out. X minus 3 minus 3i. X minus 3 plus 3i. And x minus 2 squared. Multiplying the two imaginaries and two reals together would be your first step here. But before we do that, let's just get rid of the parentheses inside the parentheses. And I'm also going to expand this so I know what I'm multiplying out there. All right, now let's multiply the two imaginaries together. And multiply the two reals together. Now we can combine some like terms here. So the 3ix and the 3ix will cancel. The 9i and 9i will cancel. Then plus 9i squared. The minus 9i squared turns into plus 9. So I can rewrite q of x as x squared minus 6x plus 9 times this. And we still have quite a bit of work to do here, but it's looking a lot cleaner. Distributing x squared. Distributing negative 6x. And distributing 18. Which finally brings us to our final answer of x to the fourth. So x to the fourth. Negative 4x cubed minus 6x cubed is minus 10x cubed. 4x squared plus 24x squared plus 18x squared is 46x squared. Negative 24x minus 72x is minus 96x plus 72. And that is the first 2 days of section 2.4.